Alrighty, this is Stephen Redfield, the instructor for the class. I was just going to run through the solutions for quiz 1 now that you guys have finished it. As far as the first problem, is two problems on the blackboard. It's really just definitions, so I'm going to go through it pretty quick. This one obviously doesn't correspond perfectly, but the solutions are the same, so it shouldn't make that much of a difference. So we'll start with the first one, which is internet. The definition of the internet for us is a system connecting multiple networks, each of which may use a transmission technology that is different from the other. So it's interconnecting different transmission technologies. So we'll go ahead and mark down X for that first one. Second one we have is network, a system for connecting computers using a single transmission technology. A network protocol is, any network protocol is rules that define the format and order of messages sent and received among network hosts and actions. The transmission rate is the maximum number of bits per second that a transmission device can push onto a transmission medium. The end-to-end delay is for an individual packet. The sum of times for processing, waiting in queues, actual transmission, and propagation over the transmission medium, so S. Propagation speed is, if I can get down to it, there it is, the rate at which bits travel through a transmission medium, literally distance over time. Average throughput is the end-to-end speed over a period of time in bits per second on a path between two hosts. So the full end-to-end speed all the way through. So that's O. Statistical multiplexing is here. It shares a transmission medium on demand by packet switching amongst multiple hosts. Hopefully it does it intelligently so as to most optimally use the transmission medium available. Time division multiplexing, the definition we gave was sharing a transmission medium among multiple hosts by circuit switching in equal time slices. So one person talks, and then another person talks, and then another person talks, and it goes back to the first person. That's time division multiplexing. Frequency division multiplexing is sort of the same thing, except instead of sharing time slots, we're sharing frequency slots. So that would be here. Shares a transmission medium by dividing the link's bandwidth among multiple hosts. So it's dividing the link's bandwidth. RFC is a public database, it's way down there, containing adopted networking and internetworking standards. That's the one where you go and you can look up multiple standards and get all the details and how it's all written up and every little measly piddly little thing of each protocol out there. User datagram protocol we gave was the connectionless protocol used often in streaming services. Definition though is an internet protocol that provides connectionless, unreliable data transmission. So that's A. TCP is a connection-oriented, reliable data transmission. So we would find that here. B. Internet protocol that provides connection-oriented, reliable data transmission. Denial of service, denial of service attack. This is where multiple hosts all try to overwhelm a server. So an attack involving multiple hosts sending continuous requests to a server so that legitimate clients cannot access the server. Basically, the server gets so busy dealing with all the phony requests that it doesn't have enough processing power to handle the real requests. A port is a number assigned to a process. A socket is an internet address combined with a port. The RTT for round trip time is what it stands. time for a small packet to travel from client to server and back. So when we're pinging, we're kind of measuring round trip time. Caching, we said, was temporarily storing data in a place where it can be accessed more quickly. So if you're going to reuse that data, you save it on your home computer so that you don't have to repeatedly download it from the internet. Cookie is there it is. History information stored at a client host to be used for later communication with the same server. Important note there, it's history information, not the temporarily, not just a strict any kind of data that caching is. And DNS we have is the application layer protocol that resolves domain names into IP addresses. So as domain name service, we have it as I. Moving on, the next problem we had in the Internet Protocol stack, if layer 1 is the physical layer, what are the other 4 layers? So working our way up, we have the link layer, the network layer, the transport layer, and finally the application layer. We're still in base definition kind of stuff here, so these all should have been pretty quick for you guys. A transmission rate of 1 megabit per second. 1 mega, this is a decimal prefix because we're dealing with rates here, networking rates. So 1 meg is 1 million, so 1 million bits per second. Now a file size of 1 megabit, and that's a binary prefix, you know that because of the I, contains how many bytes? Well, that's going to be 2 to the 20, 2 to the 10 is kilobits, 2 to the 20 is megabits. So we're going to have, I don't know if it'll even fit here, 1,048,576 bytes. So 1 megabyte is 1,048,576 bytes. To get it in bits, you multiply that by 8, so 8,388,608 bits. Now we start to get into more conceptual stuff rather than just definitions. So here we are given 2 separate transmission links, each having 2 users connected. The links have equal bandwidth and transmission rates, but link 1 or link A is using circuit switching and link B is using packet switching. So if the first user is the only one that's transmitting on each of the links, in circuit switching you're not sharing the additional unused time. So your maximum utilization is if the one user that's using it is using all of his half, so then you get a maximum of 50% utilization. But for packet switching, you're intelligently distributing the effective bandwidth time slots. So link B, for link B, the host that's transmitting all the time is allowed to use that medium for the full amount of time. So maximum utilization there would be 100%. But now we're considering both users are transmitting on both links, and we're going to also assume here they're both transmitting as much as they can. So will the average throughput of data be the same for both links? And this one's kind of tricky, but the answer is no. The reasoning here is that the packet switching network has overhead from the packet header. If you recall, for packet switch networks, you have the data that you're transmitting, and then you have your header that you've stuck on front of it. Now, this would be the packet, but for like the circuit switch network, this whole block is data. I'm going to draw this up here. For the circuit switch network, you have full block of data. For the packet switch network, you have a header and then data. So this part right here we consider overhead. So because of the packet header overhead, the average throughput of data, not header information, but data, will be less for the packet switch network in this case. Now moving on, the DNS protocol usually uses the UDP transport protocol. Now let's see at the other answers why not. First of all, FTP is not a transport. File transfer protocol is an application layer protocol, not a transport layer protocol. Same for simple mail transfer protocol. It's a application layer. TCP is actually a transport layer protocol, but because of the additional overhead and the requirement to establish a connection and the decrease in throughput of TCP, because of all the additional information that goes into the header, and for other reasons that we covered in the discussion board and in the lecture slides, and are also covered in the book, it basically uses too much transfer of information. So UDP is more streamlined for this type of service, so UDP is what's used for DNS. So the answer to that one is A. Now, we wanted to look at the mail protocols. We had 4 questions. We wanted to know if either of these, POP3 or IMAP, are push protocols. And the answer is no. They are in fact both pull protocols. They both take the information down. The other 2 questions were which one downloads to the client and either deletes it from the server or saves a copy on the server. POP3 is the one that does that. And then which one maintains the client's history and entire email directory structure on the server, and that is IMAP. So neither are push protocols, both are pull protocols. POP3 downloads to the client and either deletes from the server or saves a copy on the server, and IMAP maintains the client's history and entire email directory structure on the server. Moving on, we finally get to the last question here, and I know this quiz review is going pretty quick, but it's totally fine for you to post questions. Piazza is probably the best place if you do have any questions about how any of these problems are worked. But for now, we'll work this problem. So we are given a transmission medium with a propagation rate of 2.5 times 10 to the 8th meters per second, so fairly close to the speed of light. There's multiple computers sharing this link, and it's using packet switching, and each packet contains 1500 bytes. That's including header, data, everything. Now we're going to assume that queuing is necessary only for transmission. So all the packets have already been processed. We're just looking at queuing stuff here. So they've all been processed before entering the transmission. So obviously we're going to ignore processing delay. The distance to the destination, this is our D, is 1,000 kilometers. So here we have S is equal to 2.5 times 10 to the 8th. D is equal to 1 times 10 to the 6th. L is equal to 1500 times 8. See, this is 1500 bytes. L we usually look at in bits. So put it up here. Our L is going to be equal to 12,000 bits. If I did that math right. Should be right. Good. I'm not crazy. Okay, so now that we've established those, we can figure out these other ones pretty quick. Here is R1, and here is R2. So our R1, for the first column here, the rate of transmission is 10 megabits per second. So that's going to be, I don't even have room. I'll write it over here. R1 is equal to 10 to the 7th, and R2 is equal to 10 to the 8th. That's this 100 megabits per second. So what is the transmission delay for each packet? Well, transmission delay is L over R. So for the first one, it's L over R1. So we have 1.2 times 10 to the 4th over 10 to the 7th gives us 1.2 times 10 to the minus 3. That's 1.2 milliseconds. Now I'm going to erase just this portion so that I can do it. Fortunately, this is a YouTube video, so you can back up if you miss something. For the second one, we want L over R2. So we have L is still 1.2 times 10 to the 4th, but R2 is 10 to the 8th. So now we have 1.2 times 10 to the minus 4, 0.12 milliseconds. What is the propagation delay? Well, propagation delay we dealt as d over s. Since r is not involved here, just d and s, both of these answers are going to be the same. So the propagation delay is independent, in this case, of the transmission delay. So our d was 10 to the 6th, that's from right here. Our s is 2.5 times 10 to the 8th. So we're going to get 1 over 2.5 times 10 to the 2nd, which gives us 4 milliseconds. Next question is what is the queuing delay for the third packet. Now remember that the queuing delay for the first packet we're assuming to be 0. So dq 0 is equal to 0. It moved some stuff around, but I'm not going to pay attention to it. Sorry about that. Not sure what happened. It was from the above stuff anyways. Our dq for the first... dq for the first packet is 0. We're not dealing with 0th packets. So our dq for the first packet is 0 seconds, because there is no queuing delay for the first packet, because it's the first packet, it gets there, it doesn't wait, it's just transmitted and then propagates through the network. But the queuing delay for the second packet is equal to the transmission delay for the first packet, which up here is 1.2 milliseconds. So then dq3 is equal to dq2 plus d trans 2. So this is 1.2 plus 1.2 gives 2.4 milliseconds. Oftentimes when we look at queuing delays, we look at the queuing delay for all the previous packets plus the transmission delay for the most recent packet. So now for the 100 megabit per second case, I can just write dq3 dq3, the queuing delay for the third packet, is equal to dq2, the queuing delay for the second packet, plus d trans 2, the transmission delay for the second packet. The queuing delay for the second packet is d trans 1. So here we have d trans 1 plus d trans 2. They're the same size, so they have the same transmission delay. So 0.12 plus 0.12, we have 0.12 milliseconds. Or sorry, that's wrong. 0.24. milliseconds. Now what is the end-to-end delay for the fourth packet? Now, the end-to-end delay is a little more complicated, so we're going to look at the preceding packets. We're going to say the end-to-end delay is the queuing delay plus the transmission delay plus the propagation delay. So d end-to-end is dq, and here we're dealing with fourth packet, dq4 plus d trans 4 plus d prop 4. Now we can build dq4 off the previous dq3, which we just calculated. So I'm going to erase this so that I have enough room to write. The end-to-end delay for the fourth packet is equal to the queuing delay for the fourth packet, which, since we have the queuing delay for the second packet, the third packet we can build up and we get 3.6 milliseconds. That's just the transmission delay for the first packet plus the transmission delay for the second packet plus the transmission delay for the third packet. 1.2 plus 1.2 plus 1.2 equals 3.6. And then we have the transmission delay for the fourth packet, which is 1.2 since they're all the same size, length. And then finally the propagation delay, which we had just above, 4 milliseconds. Altogether, that is 4.8 plus 4, 8.8 milliseconds. Cool. Now we're going to deal with the 100 megabit per second case. dq4, we could build up again, is just dq3 plus d trans 3. We get 0.36 plus the transmission delay of the fourth packet, same here, is 0.12 plus the propagation delay, which is still 4. We get 4.48 milliseconds. Finally, we're talking about the average queuing delay for the first 10 packets. So I'm going to write out one after another the queuing delays. I'm going to deal with this case first, the 10 megabit per second. And remember, the queuing delay of the first packet is 0 because it goes right into transmission. Queuing delay for the second packet, 1.2. Queuing delay for the third packet, 2.4, etc., etc. On to the queuing delay for the 10th packet, which is going to be 10.8. And we're going to add those up. Since to do the average, you do the sum, then divide by the total number. You add those up, you're going to get 54 milliseconds. That is the sum from n equals 1 to 10 of dq n. And then we're going to divide that by 10 here. So we take 54, we divide it by 10, and we're going to get 5.4 milliseconds as the average queuing delay for the first 10 packets there. Now for the 100 megabit per second, you're going to see a big difference here because the queuing delay is directly related to the transmission delay. The queuing delay for the first packet is 0. Queuing delay for the second packet is 0.12. For the third packet is 0.24, and then etc. on up to 1.08 is going to give a total sum of 5.4 milliseconds. Then we got to divide by 10 again, and we have 0.54 milliseconds. Okay, that covers every question on the first quiz. If you do have any questions, please post them to Piazza and I'll get to them just as fast as I see them, pretty much. And also, I hope you all did well. We're going to start grading them now. Thank you for watching. I hope this helps you with the class.